Hello, everyone, and welcome. Thanks for joining this session. It's on one of my favorite topics, mitigating thermal bridges in passive house construction. My name is Gabrielle Brainard. I'm an enclosure specialist with SOM, Skidmore, Owings & Merrill in New York City. And today we'll be hearing from Cody Akira Belton. Cody is a passive house specialist and a building envelope consultant with Morrison Hershfield in Vancouver, BC. Cody's presentation is titled The Future of High Performance Window Installations. And he'll be discussing high performance window installation techniques that can reduce wall thickness, reduce embodied carbon emissions, meet passive house performance requirements, and potentially provide some cost-effective solutions for developers. While Cody is presenting, please type your questions in the chat. I'll be keeping my eye on these and adding them to our discussion after the presentation. And with that, I will turn it over to Cody.
Thank you for the nice introduction. Hello, everyone. So let's dive right in here. So the agenda, what we're going to be covering today is first on how to increase productivity in commercial buildings. And then I'm going to dive into a case study with a building called 825 Pacific Artist Hub. Then I'm going to give you some background information on thermal bridging at large buildings. And then I'm going to swing back into a post-construction research study that was based on 825 Pacific Artist Hub. And then we're going to finish off the presentation with window install optimization techniques. So before getting into the case study, I wanted to mention how passive house design principles will improve work productivity, allowing occupants to focus with less distractions from better soundproofing, reducing street noise, with better indoor air quality, and enhance the occupants' perception that they are indeed comfortable and can focus on the task at hand at their office. So this all can be achieved with the isolator. This is an invention from 1925 by science fiction writer Hugo Gernsback. He felt absolutely plagued with distractions in his office and decided enough was enough. The isolator mass construction followed passive house design principles. It has thermal insulation as a vibration buffer. It has high performance vision area. You can see with his goggles. It has an airtight enclosure, thermal bridge free design with constant controlled clean air supply. Even the exhalation ports have similarities to heat recovery ventilation cores. And as a bonus, this looks great with any outfit. But I know mass can be a polarizing subject as we've seen as of late. So we need to find a more practical solution to increase productivity in the office. So an alternate option is just to build a certified passive house. You can convert the whole building enclosure into the isolator. You can control interior conditioned air with a heat or energy recovery ventilation system, which supplies constant filtered fresh air, exhausting CO2 buildup, and airborne viruses. So that's exactly what we did for 825 Pacific Artist Hub. This building was completed in the fall of 2021. It's located in downtown Vancouver, BC, Canada. So this building is 7 levels plus a 1-level basement that is non-combustible construction that came with some new challenges due to high-rise requirements for building enclosure design, and is currently the tallest certified passive house commercial building in Canada. It's owned by the City of Vancouver and will be operated by a not-for-profit affiliate. So for those of you not familiar with Vancouver or the downtown core, this is roughly where the site is situated at the corner of Pacific and House Street, just off of False Creek. So here I've listed the building enclosure facade highlights. The window system thermal resistance is R7.8 effective, and the 17-inch thick walls are R42 effective. The facade design and whole building mitigated heat loss at thermal bridges wherever possible, and achieved a great final air tightness result at 0.19 air changes per hour. So the walls above grade have a split insulation system. The primary thermal components include 8-inch exterior mineral wool insulation. They use AYOC K1200 cross-fix brackets for the cladding attachment, and they have R22.5 mineral wool insulation in the steel stud cavities. So for 825 Pacific, MH used a 3D thermal simulation tool for the Clearfield wall to accurately determine the R value for the energy model in support of certification required by the Passive House Building Certifier. So the 3D thermal simulation was needed because the steel stud framing and the cladding attachment brackets impact the heat flow that cannot be accurately captured with other methods in 2D. So the differences between 2D and 3D thermal simulation can be significant to thermal transmittance and also interior surface temperature. So here are some construction photos of the wall installation in progress. The top left photo gives you a general sense of how the AYOT brackets are laid out. And the photo to the middle of the top is a closer view of the AYOT brackets over the air and moisture barrier, which is a 3M product. And then on the top right photo, you'll see the horizontal rails installed over the brackets, ready for the cladding attachment. And the bottom left photo gives you a sense of how the through-wall flashings were designed, which integrated a fabric reinforced self-adhered membrane. And the bottom middle photo has the 2 layers of 4-inch thick mineral wool insulation installed. And then the bottom right photo is just give you an idea what it looks like from the inside of the steel studs before the drywall was installed. So Passive House certified triple glazed fiberglass windows by Cascadia were specified, and overheating risk was reduced by changing the solar heat gain coefficient from 0.55 down to 0.27. So Cascadia's fiberglass frame material is combustible. So to install this in a high-rise building, the design had to comply with building code requirements to reduce the chance of fire spread between neighboring windows. So the architect's adjustment to the window-to-wall ratio compiled with additional life safety building code requirements, and all of this satisfied the City of Vancouver's building department. And here are some photos of the window installation detailing. So the window frame is positioned about 5/8 of an inch into the steel stud backup wall rough opening. The bottom left photo shows a continuous metal support angle that was needed at the sill to support the window dead load. So later, we're going to dive into a post-construction research study on how improving this window installation to reduce heat loss can impact the rest of the building. And also, if you look at the top right photo, that gives you an idea of what it looks like from the inside. So once the pre-stripping was wrapped into the rough opening and the window was installed, that 5/8 of an inch where the window set into the rough opening provided substrates on each side of the frame and the rough opening to put a rod and caulk seal, which matches conventional construction practices. So for this project, an early stage study conducted by the project architect, IBI Group, refined window-to-wall ratios on all facades and changed the window layout to eliminate narrow windows to decrease heat loss at the window-to-wall transitions. So due to limited views towards the north, facing an adjacent hotel, the design team decided to locate the stairs, elevator core, and the service rooms along the north facade, shown on the bottom left elevation. So this suited energy conservation strategies by minimizing windows on the north side, reducing heat loss, and improving overall window energy balance by maximizing solar heat gain on the other facades. So typical of all high-rise buildings, the majority of building enclosure area will be the above-grade walls, which is 51% of the total building enclosure surface area. So the as-built design ended up with 11% windows based on the total building enclosure surface area, but they caused 32% of the heat loss through the building enclosure. So besides the exterior doors, windows are the only component that disproportionately increase heat loss relative to the surface area because of the windows' poor thermal performance compared to the well-insulated walls, roofs, and floor assemblies. So this is why early stage studies to reduce window-to-wall ratios is an effective strategy to conserve energy. But just like any other building, windows are integral. They connect us to the outdoors, they transmit natural light, and they allow for passive solar gains. But to improve building energy performance, we need to pay more attention to the window's placement. And that is the recommendation we give on all our projects. So once window-to-wall ratios and the building enclosure assemblies were established, the project team needed to adjust thermal bridges to account for all heat loss through the building enclosure. So thermal bridges accounted for about 15% of the heat loss through the building enclosure. So this is a large piece of the pie considering all thermal bridges were mitigated in the design. An accurate determination of thermal bridge values for the energy model was a significant factor to the overall building design in support of Passive House building certification. So using inaccurate thermal bridge values would have unjustly inflated space heating, cooling, and the primary energy renewable demand, the total energy, which may have led to even thicker external walls. So like the Clearfield wall, a 3D thermal simulation tool was used where the steel stud framed wall and the cladding attachment clips impact the heat flow that cannot be accurately captured with other methods in 2D. So this bar chart shows the breakdown of each thermal bridge and its relative impact to the building's heating demand at 825 Pacific. So the window to wall transition thermal bridges have the highest impact, as you can see with the bar on the far left. And this signals where improvement should be focused if needed, because basically all the other thermal bridges on the project combined almost add up to this one window to wall transition thermal bridge. So really this is the low hanging fruit where you'll see the most benefit out of optimization or improvements to that detail. So high impact thermal bridges are typically the ones with the largest length or quantity. Window to wall transitions often have the largest interface length as shown with the red bar on the bottom right. So windows significantly outweigh all the other lengths of thermal bridges at 851 meters for this particular building. So now I'd like to review some of the thermal bridges at 825 Pacific and what we did to mitigate the heat loss. So this project used an inverted roof system with 8-inch thick XPS rigid insulation that had numerous penetrations from screen posts that surrounded the mechanical units on the rooftop and rooftop anchors at the various terraces and upper roof. And the general contractor, who was Legcor, their superintendent reported some positive feedback using the Armatherm thermal brakes. So Legcor sent Armatherm the size and bolt locations, so all the thermal brakes arrived on site with pilot holes ready for installation. So in MH's experience, Armatherm thermal brakes should be minimum 2 inches thick to have a meaningful impact to mitigate thermal bridge heat loss. And at the front entrance vestibule, which is outside of the conditioned thermal space or thermal boundary, so if you take a look at the photo on the left, the vestibule concrete curbs were placed on the left and the right of the vestibule, so the concrete floor slab could be placed directly over the 8-inch XPS roof insulation above the heated basement to mitigate thermal bridge heat loss to only the curbs instead of losing heat from the entire slab if that was placed directly over top of the basement. And for the typical footings, because we have a raft slab, the structural engineer didn't want any insulation to be, or the footings, or the mass amount of weight of this building to be bearing on anything but concrete or the soil. So to mitigate heat loss, we needed to extend the vertical insulation as far down the foundation wall as we can below the slab on grade junction, which is about 5 feet in this project. And that was with 5 inches of XPS on both the interior side and exterior side of the foundation wall. And we used the same strategy at the footings around the elevator core, which is very similar detailing with 5 inches of XPS on the inside and outside of the foundation walls, running down and basically stopping at the top of the raft slab. The ground floor base of wall detail eliminated through-wall metal flashings to mitigate the thermal bridge, so similar to what we saw before on the upper through-wall flashings, where basically we used a peel and stick membrane flashing that sloped away from the building with a tapered mineral wool insulation, and trying to install that insulation to have no voids or gaps. And then with the parapet wall or curbs, when we were on site, we wanted to verify that rigid insulation was installed over the parapet walls prior to the vapor peel and stick membrane to maintain thermal continuity. And the thermal bridge correction factor is a negative psi value in this case because the heat loss has been overestimated. The length of the roof and the wall assembly are external dimensions, so over accounting the clear field areas which overlap at the corner. So conversely, the inside corners will always be a positive thermal bridge for the opposite reason, where heat loss is generally underestimated. So in the end, 825 Pacific Artist Hub achieved Passive House certification awarded by the Passive House Institute. So now I'm going to dive into some background on thermal bridging at large buildings. So thermal bridges are a big deal. They can impact your heating demand and your total energy demand, which is PER. It can impact occupants' thermal comfort. It can impact both the occupants and the building itself's health and durability. And thermal bridges will definitely impact our choices for materials and construction. So for those of you not familiar with assessing thermal bridges to determine what is a good, bad, or ugly value for linear transmittance, this table gives you a general sense of the range. So Punch Windows default install thermal bridges are set at 0.04 watts per meter Kelvin in both design pH and PHPP until it's refined by the pH consultant. So good window insulations can reduce the thermal bridge to less than 0.01, while bad detailing can lead to values above 0.1. Now, when you're dealing with high-rise building construction, you're going to deal with higher structural loads. You're going to use stronger materials like concrete and metal, and windows tend to be aluminum framed. They need to pass higher wind load requirements, water penetration tests, and air tightness requirements. These larger buildings also have more stringent requirements for code and life safety, so generally they need to use non-combustible components. And for cladding attachment systems, we need to focus on reducing thermal bridging, and they also need to obviously support the structural loads for the cladding dead load and wind load. So considered as a secondary structure with influence on thermal performance, we must evaluate our cladding attachment system based on both structural and thermal performance. So cladding selection and layout will influence the rail orientation and bracket spacing determined by the facade engineer. So this is just one example showing the differences in performance between the same wall facade with vertical oriented rails versus horizontal on the right. So if you look at this table at the bottom here, essentially, if you were to just switch the orientation to horizontal, we see a slight improvement in effective R value from the vertical rail going from R24.1 to, if you were to orientate it horizontally, we can get up to 25.4, so a 6% increase in R value. So as previously mentioned, high impact thermal bridges are typically the ones with the largest length or quantity. So for multi-unit residential buildings, balconies often have the largest interface length that must be considered early in the design stage to mitigate heat loss. But for office buildings that generally don't have balconies or a limited amount of balconies, the intermittent floors often have the largest interface length that must be considered early in the design stage. But for all large buildings, the window to wall transitions have the largest generally have the largest interface length, as shown with the 825 Pacific case study. So now I'm going to shed some light on thermal bridging analysis. So thermal bridge values are determined for both conventional and passive house projects. And the truth is, thermal bridge determination methods are not enforced by current building codes in Canada, US, or the Passive House Institute. So conservative assumptions for a thermal bridge value is basically a guess with an additional buffer for uncertainty. So utilizing accurate thermal bridge values determined by a custom thermal simulation entered in the energy model can actually generate energy savings compared to using a conservative assumption. So this will make meeting energy performance criteria easier. So practitioners should be aware of the importance of accurate thermal bridge values for high impact thermal bridges, where these more precise 3D thermal simulations can provide a better assessment of thermal transmittance and interior surface temperatures for condensation and mold risk assessment. So often 2D thermal simulations is good enough, but it's important to recognize when 3D thermal simulation is needed. And CSA Z5010 can be referenced to provide some general guidance on this. So insulated opaque glazing spandrels for curtain walls is an example where there is significant lateral heat flow through the aluminum framing and the metal backpans that are not fully accounted for in the 2D thermal simulation. So insulated curtain wall spandrel assemblies evaluated in 2D can significantly overestimate the thermal performance compared to what is measured in hot box tests. A 3D spandrel model can directly capture the lateral heat flow and can provide results within about 5% of the measured guarded hot box values. In this particular research study, the 3D spandrel model matched the guarded hot box thermal transmittance value, which showed a 0% difference in the results. And for building enclosure consultants and architects, the accuracy of our thermal simulation tools is crucial, and 3D thermal simulation is needed for certain components and connection details. So here's an example of a wall assembly with a bracket and rail cladding attachment system. So the intermittent brackets increase heat flow. The steel studs in the backup wall also increase heat flow, creating two types of thermal bridges in one direction. But a single 2D section cannot fully represent the heat flow through the assembly for the intermittent bracket. So how can we calculate the effective Clearfield R value for this wall? So there are three methods to determine the effective Clearfield R value using 2D. So the first is the average volume using exterior assembly conductivity average based on the volume of components. There's the second option using equivalent conductivity, where basically the conductivity of brackets are based on an area weighted average of the bracket and insulation. Or option three, linear and point transmittance, where the bracket and rails are modeled separately in 2D and combined with the 2D Clearfield assembly. So if you refer to the column on the far right, you can see how each method using 2D methods compared to a 3D simulation for the same wall assembly. So the FRP, which is fiber reinforced plastic, these brackets show slightly overestimated results using the equivalent conductivity method, increasing the R value by 1%. But the very same method used for aluminum brackets instead of the reinforced plastic, the R value is decreased by 41%. So ultimately, all three of these methods using 2D for this wall are inaccurate compared to the 3D thermal simulation and shouldn't be relied upon. So 3D simulation captures lateral heat flow and will often show different temperatures compared to 2D simulation. So 2D simulation calculates average temperatures at best, but the coldest temperature is what counts for evaluating the risk of condensation. 3D thermal simulation really better reflects reality and is sometimes needed to avoid mold and condensation buildup on the building enclosure's weakest component, which is the windows. And the Passive House Institute does not provide guidance to define when 3D thermal simulation is appropriate to generate accurate results. So the Canadian Standards Association released the first edition of CSA Z5010 in 2021. So this standard provides general guidance to determine what thermal simulation method, 2D or 3D, is acceptable depending on the building transition complexity and the desired output. So currently CSA Z5010 has not been adopted by any building codes in Canada or US to standardize how thermal simulation methods are calculated. But owners and project teams developing a passive house building need to be aware of this lack of requirements to calculate our thermal bridges. Now on to some thermal bridging resources available to us. So the first one is the Building Envelope Thermal Bridging Guide that was developed a number of years back, and it's publicly available for download at BC Housing's website. And so this now includes over 600 building details with thermal performance information and gives you some ideas on how to detail some of these transitions. And this entire catalog has now transitioned into thermalenvelope.ca, which is very user-friendly. And I refer to it on a lot of projects when, especially at the beginning stages of projects, when you're looking at clear field assemblies and some of your important transition details. And another option is also when you get components certified as a certified passive house component in the passive house database, they'll often have some psi value and chi value information on, depending on the type of thermal bridge that it is. So this is just an example of a window component certificate that includes 3 window install options and the calculated psi values for each of those installs. So Morrison Hirschfield conducted a post-construction research study based on 825 Pacific to review a common energy conservation strategy that led to its 17-inch thick super insulated wall assembly. So the strategy is to add excessive insulation to the external walls to compensate for heat loss born from high impact thermal bridges. So this can be explored in the energy model, but typically revealed diminishing returns to the overall thermal performance. So by taking this path, we're really adding insulation material to lower operational carbon while increasing embodied carbon and potentially diminishing marketable floor area in the process with thicker wall buildups. So a more effective energy conservation approach is to allocate resources to reduce heat loss at high impact thermal bridges that can be optimized. So this should be explored on every project. So you could start with a review of thermalenvelope.ca or another trusted source to find a thermal bridge detail, or produce a custom thermal simulation of a high impact thermal bridge. So we analyzed 2 different window install designs for 825 Pacific, the as-built versus the optimized install. So the study objective was to determine if the high impact thermal bridges at window to wall transitions can be optimized to provide a trade-off opportunity with the external walls to reduce its 17-inch thickness. A trade-off that produces nearly equivalent energy performance and provide an impact to usable commercial floor area, construction cost, and embodied carbon emissions. So the next question is, how do you optimize a window install? What reference documents are publicly available? So here's one thermal bridge reference example from thermalenvelope.ca. So this install uses a metal support angle at the sill. But this should be used with caution because it might not be suitable for your project. A structural analysis is needed to determine what the window size limitations are for based on this connection detail, and if the design can sustain the project's wind loading, which is generally a problem as you get to larger and taller buildings. So the second option is to reference thermal bridging data from the Passive House Certified Component Certificate. But does this install match your design intent? Will it be acceptable to the Passive House Building Certifier? And just looking at this example certificate here, what are the material thermal conductivity values? Because none are listed. And will this match our wall assembly design? It's kind of unclear because we don't even really know what these materials are. It says that it's an EFIS system, so based on the color of it, I would assume that's a concrete wall and has a bunch of exterior rigid insulation on the outside. But also, more importantly, in reality, how do you support the window's dead load and the wind load when projected over exterior insulation? So when you take a closer look at this image of the windowsill and head detail, the window is positioned completely over the rigid insulation. So we really have no idea how this is connecting back into the backup wall structure. So, although these numbers might look great for, putting into our energy models, but does it really reflect of what's going to go on site once we get our shop drawings, the facade engineer designs how these windows are going to be installed? Will it work? So if a window installation method is not available, we recommend retaining a qualified consultant team to develop a solution customized to suit your project. So the development of a window installation suitable for non-combustible construction should consider moisture management, airtightness, durability, thermal performance, structural support, fire protection, constructability, and of course, cost. So considering the limited thermal bridge references suitable for larger passive house buildings, we wanted to help provide an open source data that any project team can use. So thanks to a generous Building Excellence Research Grant from BC Housing, MH is working towards delivering innovative solutions that will be added to thermalenvelope.ca for any project team to use. So this partnership with BC Housing provided the kickstart MH needed to develop a real solution that is suitable for all building typologies, including non-combustible high-rises. So Morrison Hershfield, we're comprised of a multidisciplinary team with the necessary consultants required for this research project. So due to the depth of knowledge and number of capable consultants at Morrison Hershfield, we really had no challenges to develop a cost-effective window installation solution. So this solution was vetted through building enclosure, facade, and 3D thermal simulation teams to make this solution market ready. So today, I'm honored to present for the first time in the US a shift into the next generation of high performance window installations to simply make buildings better. Introducing Akira Window Connection by Morrison Hershfield. This is our steel stud backup wall option. So to show you how this will work, I'm going to go through a little windowsill sequencing detail. So because this was based on our 825 Pacific Artist Hub case study, we wanted to use the exact same backup wall system. So this is 2x6 steel studs at 16 inches on center, which were 16 gauge. So once that's framed up, we're going to install our exterior 5/8 dense glass. We're going to line the rough opening with 3/4 inch plywood. We're going to install at the edge of the sill, and just the sill, we're going to install this continuous aluminum angle. So in a lot of conventional construction, this is used as a back dam for water ingress management. But in our case, it's used as part of the wind loading system to connect the window to. And mind you, these are isometric images captured from our 3D thermal models. So they don't actually use any membranes or any products that don't have any impact to thermal performance. So, although we're showing our brackets installed here directly over the dense glass, just please note that you're going to have a continuous air and moisture barrier at that interface before these brackets are installed. So the brackets, these are just generic stainless steel brackets that are positioned directly into the steel studs on the wall, spaced at 16 inches on center. Then we're putting a 2-inch by 2-inch 18 gauge galvanized steel angle over top of those brackets. And so this is going to become what we're going to be positioning our window over. So like you would do in a normal window rough opening, you're going to align it with plastic horseshoe shims, which are generally, it's going to be, the spacing is going to be dictated by the window manufacturer, but for this particular manufacturer, it was 8 inches on center. And then we're going to place our window in. And again, we're going to use that aluminum angle at the back there in the rough opening to fasten into the window to pick up the wind load. And then we're going to continue on with the cladding attachment system. So this used a larger bracket with horizontal rails. And then in the cavity directly below the window, we want to fill all those void spaces with insulation. So in this case, we decided to use a loose fill mineral wool. And then you're going to add your insulation to the exterior. So, the actual project used 8 inches of exterior mineral wool. So for this particular model, we just used 7 inches. And then to further improve and lower the psi values for this window install, we wanted to line the rough opening with 1 inches of XPS. And then when we install in the side cavities, we install bad insulation, and then we cap it off with our interior finish, which in this case is just gypsum wall board. Sorry, and just another important thing to note. So the Akira window connection shifts the window position outwards to basically align with the window frame at the window frame's interior edge with the wall sheathing's exterior face. And in this case, the window frame is over insulated in the design, which is really not imperative, as it's only providing a minimal improvement to the psi value based on the narrow window frame analyzed in this case. So we decided to use the Cascadia Universal Series window frame in this model, since we already had it previously modeled in 3D from the 825 Pacific Artist Hub project. So this just gives you a view of the underside of the install. And once insulation is installed, you can see what separates this from typical details that use continuous angles is that, similar to how we're improving thermal performance of our clear field walls by, getting rid of continuous Z-girts, because we're basically attaching our warm backup wall, which has a continuous metal bridging through our exterior insulation going to our cladding. We're avoiding that with our intermittent clips or brackets. So we're using that same principle here to support the window, where, as you can see with this continuous angle, there's a gap now between the backup wall and the edge of that continuous angle. So now we have that space where we can add our exterior insulation and butt it directly to the underside of the frame without interruptions from, high conductive materials like metal. And then we install our insulation. And then to give you an idea how the heat flow is going through this wall assembly and window transition, if you look at the isotherms, the green kind of represents the center of the wall. So you can see that at the top of the image through the IGU. So really we want that to flow seamlessly into the wall with not many interruptions, because that's basically visually signaling where there's heat loss happening. So because we have the angle pushed a little bit outwards towards the left, we can allow that heat flow to gently transition into the exterior insulation, as you can see with the green flowing behind that continuous aluminum angle, or steel angle in this case. And this is giving you an idea of one way to install the air and moisture barriers. So the way I would see this being done is, if you can picture this window and the support system, not installed yet, you just have your rough opening. So you're going to line it with your peel and stick membrane. So that's this blue hatched area you see here. That's going to wrap up and over your aluminum angle in the rough opening. And then once you have your support system installed and the window installed, you can now attach this green tape, which is, a high performance air barrier tape, which is going to connect your pre-stripping along the rough opening to the window frame. And then in the field of the wall, shown in this orange hatch, is your typical air moisture barrier membrane. And this is how we're going to maintain air barrier continuity at this transition. So the facade team at MH conducted a detailed structural analysis of a Akira window connection. So table 1 shows the maximum intermittent bracket spacing required to support various window heights. So a 12-pound per square foot triple glazed window that's 12 feet tall can be supported by brackets spaced at 16 inches on center. So for this analysis, we assumed that 100% of the window dead load is distributed to the continuous angle and to intermittent brackets at the windowsill. And 100% of the wind load is distributed to the continuous metal sill angle on the rough opening and to intermittent metal strap anchors at the window head and jambs, which is typical of most rebate style windows. So table 2 shows the maximum window width and height based on the design wind load. So at 825 Pacific Artist Hub, at 7 stories, would fall under the second column where the windows could be 12 feet tall with an unlimited width. The window schedule for 825 Pacific has varying window sizes. So the images on the bottom here should give you an idea of how many intermittent brackets would be required based on the window's width and height. So for example, the bottom left image is the largest window on the project, which was about 11 feet, 2 inches tall. So this would require 7 brackets to support that window's dead load. But then as you get to the smaller windows, we can actually increase the spacing, and if needed, it could get away with 3 brackets, as you can see with the windows on the far right. Now to dive into the window head install sequencing. So again, we're going to start off with our 16 gauge 2x6 steel studs, spaced at 16 inches on center. We put on our 5/8 dense glass. We line the rough opening with our plywood, 3/8 plywood. We're going to put on our wall brackets at some point to support our cladding. We have our horizontal rail system to support our cladding. Then our windows are going to be installed, and that shows you an example of one of the strap anchors, what they use for Cascadia windows. And then we're going to install our multiple layers of exterior insulation. So in this case, the goal was to produce the lowest psi value possible. So we did, again, over insulate the frame with the exterior insulation. And we also lined the rough opening again with 1-inch XPS. And that's for, the sill, head, and jambs. And then we're going to install our interior batt insulation, put on our interior finish, which in this case, again, was gypsum wallboard, and that's it. And so typical for our jamb and head details, you're generally going to have better psi values because we don't have to deal with the dead loading support that we do for the sill detail. So you can see how seamlessly the green in the IGU flows seamlessly into the exterior wall insulation. So again, I just wanted to give you an idea of how the air and moisture barrier could be installed for this project. So you can imagine prior to the window being installed, we're going to use that light blue membrane, which is likely going to be a vapor impermeable self-adhered membrane, or peel and stick, or whatever you want to call it. And that's going to line the rough opening as pre-stripping. And then we're going to install the window itself. And then we can install our, shown in green here on the interior, how we're going to connect the air barriers from the wall to the window. And because, my building enclosure consulting side, I'm a little worried that this backside of the tape might not be able to handle some water that might find its way back to this transition. So I'm going to install an extra layer of self-adhesive membrane to line the wall and across the top of the window frame. And then all of this is going to be positively lapped by this orange membrane, which is our field air and moisture barrier. So for window install design options, there are 3 fundamental questions the project team should consider early in the design stage. 1, does the project window install fulfill the Passive House Institute requirements? And 2, what is the impact to the energy performance? And 3, does the window install provide design flexibility for other building components? So for question 1, the window install must fulfill the hygiene criterion. The information needed is obtained from the thermal simulation to determine the temperature factor at the coldest spot on the interior surface. So the window install must meet or exceed the temperature factor developed by PHI for the project's climate zone. So this is a moisture protection check to ensure that the window to wall transition details are planned and executed to avoid mold and condensation. So using the Akira window connection at the head transition, the minimum temperature factor is 0.76. So this does fulfill the hygiene criterion because it's over 0.7. And the minimum temperature factor is 0.81 at the sill transition. So again, it definitely fulfills the hygiene criterion as well. So note that thermal simulations for this particular project included a pH window that was rated for a cool temperate climate zone. So in table 3, we show the temperature factors for the head, jam, and sill transitions. And this variable completes the FRSI formula, so we can calculate the minimum interior surface temperature to assess the risk of mold accumulation based on the climate zone boundary conditions. So for projects located in cold climate zones, the window connection temperature factor fulfills the moisture protection criteria at the window frame edge. However, the glazing edge does not, and it's really at a higher risk of mold and condensation accumulation on the interior surfaces. So the window component and glazing should be rated for the appropriate climate zone. So this is just showing that the window connection install method is solid and actually does pass this hygiene criteria based on just the connection detail itself, but the glazing edge would not. So you definitely would need to upgrade to a cold climate window system. So the minimum temperature factor is 0.81 at the sill transition. So it does fulfill the hygiene criterion too. So note that the thermal simulation includes a pH window rated for a cool temperate climate zone. So table 3 shows the temperature factors for the head, jam, and sill transitions. This variable completes the FRSI formula so we can calculate the minimum interior surface temperature to assess the risk of mold accumulation based on the climate zone boundary conditions. So for projects located in cold climate zones, the window connection temperature factor fulfills the moisture protection criteria at the window frame edge. However, the glazing edge does not, and it is at a higher risk of mold and condensation accumulation on the interior surfaces. So the window component and glazing should be rated for the appropriate climate zone. So regarding question 2 and 3, the same thermal simulation is used to calculate the thermal bridge value to determine the building energy performance impact. If completed early in the design phase, the Passive House consultant can help explore design changes to reduce external wall thickness. So table 4 are the psi value results for the Akira window connection with the steel stud backup wall option. The 3D thermal simulation calculated excellent, nearly thermal bridge-free results at the head, sill, and jams shown in the far right column. So after running variants in PHVP with new psi values from the Akira window connection, this resulted in reduced window install heat loss, creating energy conservation savings, providing more design flexibility for us to play with. The amount of energy savings compared to the as-built scenario can be seen in table 5 in the second row. So this is an enhanced view of the second row. The limiting factor for this project, as for most large buildings, is the PER demand, or the total energy demand. By simply improving the window install psi values, we reduced the PER demand by 0.84 kilowatt hours per meter squared per year. So the PER energy savings is now a buffer providing design flexibility to reevaluate the external walls to potentially reduce insulation thickness. So by optimizing the window install with Akira window connection, we concluded the wall's 8-inch thick exterior insulation in the as-built scenario could actually be reduced to 6 inches and still achieve Passive House Classic building certification. Now, an alternate wall design with reduced insulation can have several potential benefits. We can decrease wall thickness, increase cladding attachment options, decrease embodied carbon emissions, and decrease wall construction costs. So table 6 is an isolated cost analysis in Canadian dollars on the window install methods alone, showing an increase in material cost to use a Kira window connection compared to the as-built method. So for the entire 7-story building at 825 Pacific, it would have costed just shy of $3,000 extra in material costs to go to the Kira window connection instead of the as-built method. So in table 7, we show the material cost comparison for a Kira window connection plus the exterior wall impacts. So the total cost analysis with a 2-inch decrease in exterior insulation shown in the bottom row, we realized material cost savings by using the Kira window connection upgrade. So if 825 Pacific Artist Hub was constructed today, we would anticipate to save approximately $47,000 Canadian, or about $35,000 US in material costs. So that's $2.58 Canadian or $1.95 US per square foot reduction in your opaque wall material costs. So by optimizing the window install, the exterior wall insulation can be reduced by 2 inches. So this is saving over 3,000 cubic feet of mineral wool insulation from being installed on the walls. This equates to less raw material extracted, processed, manufactured, transported, installed, and disposed of at the end of the building service life. So approximately 5.3 imperial tons of carbon dioxide equivalent would be averted. Reduced exterior wall insulation and reduced cladding bracket size is estimated to save about, again, $35,000 US in material costs. And with thinner walls, there may be an opportunity to increase interior floor area by 1.2% if realized early in the design stage, assuming no variance permitted to encroach over property setbacks due to the exterior wall insulation. So this demonstrates how we can leverage thermal simulations at high impact thermal bridges, such as window to wall transitions, to impact the overall building design and the building owner's bottom line. So digging into this Collier Vancouver office market report for Q1 of this year, it mentioned that the weighted average asking net rent is about, for a commercial property, is about $55.76 Canadian per square foot per year. So by adding this extra 246 square feet to this building, to this 7-story building, we are putting essentially an extra 13,000, just shy of 14,000 Canadian dollars, or just over 10,000 US dollars in the building owner's pocket each year. So you can imagine if this was a much larger building, this would be a substantial number that definitely would, be attractive to any building owner or developer. So aside from superior structural strength, thermal performance, and window size freedom that a Kira window connection provides, the question I have for the audience, in terms of overall window install complexity, including install options with or without a plywood window buck, and considering proper moisture and air barrier detailing, which of these two options appears simpler and faster to construct? So the detail on the left is the same one we showed earlier from thermalenvelope.ca, integrates plywood window buck to try to get that window position more or less aligned with the exterior insulation. And then that's causing us to need to use a thick steel angle at the bottom to support the window's dead load. And then this is also requiring us to have more complex shapes to wrap our air and moisture barriers around, to go from the backup wall to wrap back to the window. And you compare that to what I've shown you with the Kira window connection, where the rough opening detailing is very similar to conventional practices. So I think the adoption of this would be quite seamless for a lot of project teams. And the next step is for us to assemble some mock-ups for testing. And these mock-ups would be suitable for new construction, retrofits, prefabricated wall systems, and even modular systems. And we're also in the works of adding additional thermal bridge data for different backup wall options that will be added to thermalenvelope.ca later this year. And in conclusion, for modeling tools, you need to leverage energy models in design. You can use these to help identify high impact thermal bridges, and you need to leverage custom thermal simulations to optimize those high impact thermal bridges. So you can improve thermal performance and resistance to mold and condensation. You can potentially decrease your external wall thickness, which could potentially increase interior floor area. And this could decrease embodied carbon emissions, which means less building materials are needed for the project. So a key takeaway for owners developing a passive house building is to define thermal bridge simulation requirements at the project conception so we can allocate appropriate resources when issuing a request for proposal for architectural and engineering services. So this RFP scope of services could reference something like CSA Z5010 standard or define custom thermal simulation requirements, whether 2D or 3D thermal simulations are required at anticipated high impact thermal bridges. And the question I have for developers out there in the audience, would you rather marginally increase design soft costs with additional 3D thermal simulations to improve the building design, or increase hard costs as a result of conservative thermal bridge assumptions that you had seemingly no control over? And that's it. Thank you very much.
Welcome, everybody. Thank you so much for that presentation, Cody. I really love this topic as an architect because I feel like the case study that you presented is just like the value of thoughtful detailing and accurate analysis, and that just kind of speaks to my, building enclosure specialist heart. So just taking a look at the questions that came through the chat during your presentation, there was lots of curiosity about the Acura window connection detail, and lots of people wondering where can I get this? So maybe you could just kick it off by telling us a little more about what that is and if it's available, and sort of answering people's burning curiosity on that.
All right. Yeah. So sorry, can everyone hear me? All right. Yeah. So Acura window connection, it started off as this idea that we had, that came from this case study, knowing that there was a substantial amount of heat loss coming from the window to wall connection and how we can improve it. And then there's this BC housing grant that is available every year for, things like this, for people looking to push the envelope and innovate, make, better ways of doing things instead of just maintaining the status quo, and just to continuously develop, making our building envelopes more efficient. So as shown in the presentation, we had a team of engineers that we worked towards trying to develop a solution, and we wanted a solution that will be like open source, publicly available. And for me, I rely a lot on thermalenvelope.ca, as I mentioned in the presentation, for a lot of pretty much throughout the design process, from initial schematic design stage all the way through completion, really, if there are any needed changes in the design. So the idea was to get a better window install option that's constructible and energy efficient and structurally sound for many different building typologies, whether we're talking wood frame or we're talking masonry, retrofits, high rises using, whether it's steel stud infill walls or it's mass timber. We wanted something that was versatile, basically any type of assembly that uses exterior insulation. We believe this could be a solution for that project. And from our initial structural analysis, we found that definitely there are higher wind loads you got to deal with as you go up to something in the neighborhood of 60 stories. We haven't tested in our analysis anything beyond that, but it's definitely possible. It just kind of changes the size limitations of the window. But for right now, we are completing our analysis on a mass timber option. We have already completed the analysis on the steel stud option, which was presented here. And both those results are going to be uploaded in your standard data and result sheets on thermalenvelope.ca. So we're hoping to have all those results before the end of the year. Could be a little bit sooner, but yeah, we're pretty busy over here at MH. So we will, yeah, that is the ultimate promise and goal for the BC Housing Grant that we received for this research.
Awesome. And is this more of a proprietary product that would maybe be marketed by someone, or is it more of like a concept where someone could replicate the detail using more off-the-shelf components and then use your analysis to justify the thermal bridging?
Yeah, well, definitely the idea is that we wanted to use only off-the-shelf components. So basically what the analysis used is the same wall brackets that we used in the actual project for 825 Pacific, which was the AYOT CrossFix K1 bracket system. So it's just a smaller version. Like in the actual wall systems, they used the 200 millimeter. And for these ones, I believe it was the 76 millimeter for the window install. And so we just needed something to base our structural analysis off of, a real product that has, it's made out of stainless steel. It's got a certain gauge. It's got, certain fasteners that are, suitable for that bracket. So we want to analyze an actual system. So we could, like, if we wanted to put this in a building today, it could be done. It's not something proprietary that's still in development, although like that could be something we could look into in the future. But the idea is that we want more options available today, and more variety of options tomorrow. So if there's anybody in the audience that is involved with cladding attachment bracket manufacturers that think that this could be suitable, that they want to open up more doors for not only finding energy efficient ways of installing our cladding systems, but also window support systems, so an entire facade solution. That's who we want to be, working with to come up with customized data and result sheets for their particular product, and also uploads to thermalenvelope.ca. So it would be very user friendly for any design team, architect to go onto thermalenvelope.ca and have an array of options of different manufacturers and products they can select from, and hopefully have an array of different insulation thicknesses and backup wall options that will match their project. So they should have very accurate psi value results that they can use directly in their energy model.
That's awesome. So, I mean, I think what I hear you saying is that you're really interested in making publicly available this more accurate thermal modeling for real details that actually work. And that's sort of one of my questions is, I've looked at, the building envelope thermal bridging guide and, the thermal what's it, thermalbridging.ca, and I'm always looking for, where's my detail, right? Where's the detail that actually matches what I'm trying to do? And, architects often don't, we always want to customize something. There's always something different, and the detail you want is never really in these guides. So I guess one question is this your vision for how the guides could become, I guess, more useful for designers? And like what else, what needs to happen? Is it that manufacturers need to commit to doing this analysis and providing that information, or do you have other ideas about how these guides can be more useful to sort of real world design problems?
That is a great question. Definitely, being at 600 plus details right now in thermalenvelope.ca, like that sounds good, but like from your experience, it's not enough. They're like, we need tens of thousands of options. So like there's whatever you're trying to do, like hopefully there's a good reference detail in there already. And, with time, we will definitely get there, because it's, it's a living document that's always being added to. So just like with this Akira window connection, it's just one more thing that will be added to it that should be useful to a lot of design teams. But yeah, I definitely think like on a project per project basis, doing a bunch of custom analysis can be costly, and it doesn't make, all that much sense to do a bunch of them for individual projects. And in my opinion, the onus should be on the product manufacturers that are trying to, get us to use their systems and their products, and to put the onus on them to do the modeling. So, we have a lot more options to select from in thermalenvelope.ca, instead of, everybody working in silos in their own design teams and trying to figure out solutions for themselves. I'm hoping one day we could just have great solutions just publicly available, where we don't need to, reinvent the wheel every time we design a building. We should have great solutions available right now. And yeah, in my opinion, looking at thermalenvelope.ca and other thermal bridge catalogs, I kind of hit a roadblock with like, how do we get a really good window install, and where do I get that information? And I personally couldn't find it. So MH decided to bring a solution to market.
Yeah, it's super interesting. Yeah, I mean, maybe manufacturers who are already making some of these systems could just commit to producing the the thermal modeling that would enable them to be used in Passive House, because of course it has to also be done, per the Passive House requirements. There's one of the things I thought was interesting in your presentation is you noted that there's no standards for thermal modeling. There's many different approaches which each yield different results. It's not that physics is different, between Europe and the US, but we have different standards, and different codes might be referencing different standards, and it's kind of a mess, actually. So I wonder if you have any thoughts about standardization, and do you know of any efforts to try to rein this in, especially as we thermal bridging requirements start getting written into the code, and you have to make this information more accessible to like the general AC community?
Mm-hmm. Well, yeah, working in Canada, it's like they did develop about a year ago, they came out with the first edition of CSA Z5010. So that is a great standard that really does kind of put in black and white exactly what should dictate the need for a 2D thermal model versus what would trigger the need for a 3D thermal model. And for instance, like as soon as you deal with something that is a point transmittance, like a bracket, like that should trigger the need that it's got complex heat flows that you really can't capture accurately in a 2D model. So that's what, you really want to use a 3D model to actually capture that psi value properly. So that's what we did for our results for Akira window connection. So that's
yeah, it's great that you guys have that standard.
But then, yeah, like I'm working with the Passive House Institute in Germany. They kind of have a stance that like being conservative is okay, because at the end of the day, that might just mean you just have a better building. But we know, working in North America, that, cost drives a lot of our decisions. So if we're giving, somewhat junk information for a conservative assumption for a high impact thermal bridge, such as a window to wall installation, that could like start to inflate our heating demands and our total energy demand, which, makes our design harder to achieve the goals. If Passive House certification is the goal, we're just pushing the goalpost further away from us. So if we actually, do a favor for our design teams, get access to accurate information, such as, important information like high impact thermal bridge psi value data, that just makes achieving our collective goal a lot easier. And then what I showed in the example for 825 Pacific is that with that better install and more accurate data, we can actually start trimming up the walls. So instead of using the 8 inches of exterior insulation, we could have got away with 6. And in different municipalities, regions, like maybe that might mean that we could have increased the interior floor area. So more marketable space for whether you have condominium units, or more marketable space if you have, leasing commercial space. So there's real, just like cascading of benefits if you just, start using accurate data for your energy models. It's a pretty powerful tool that, definitely affects our bottom line, especially for developers.
It's a really powerful example, I think. And, there's also diminishing returns to additional insulation and the embodied carbon of the additional insulation and all the other things that have to get bigger as you start putting more and more, width of insulation on the outside of your wall. So I think it's a really powerful example. And of course, the physics of it are the same, right? Like it's a bit arbitrary, I guess, ultimately what the standard is to some extent. So I wonder if a couple of folks in the chat noted that thermal bridge modeling is really expensive, and I would say also a lot of people don't have access to 3D thermal bridge modeling programs. They're not maybe as accessible and as the 2D programs. Can you walk us through like your thermal bridge modeling process on a typical project? What do you model at what time? How often are you updating the models? How do you kind of dial in on the modeling in an efficient way?
It depends on the project type, but definitely like we're going to know right away what you want to identify at an early stage in the schematic design stage, hopefully, of like what are your high impact thermal bridges. So as I mentioned in the presentation, like a lot of times these are the linear thermal bridges that have the most length in a project. So if you're dealing with a high-rise condominium building, you might have a lot of balconies. So your balcony to wall transition might be a very important detail you want to look at early. And office buildings and most buildings, your window to wall transitions is going to be that like most impactful thermal bridge that you really want to do well if you want to, have the largest impact on your space heating demand. So when we were doing our initial design pH model, and I love how the newer design pH 2.0, you actually can start to implement all your thermal bridges right in there. So definitely you're going to want to have a baseline of data that you want to use. So I personally use an array of different sources, some catalogs from PHI itself and thermalenvelope.ca, and there might be a couple ones that might be missing. So we basically need to come up with something relatively accurate that we can use as placeholder values. But once you import that into your PHVP model and you start to take a look at your thermal bridge inputs in your U value folder, you should be able to see, where it's hard to like just explain it, but like when you're in the U value tab and you scroll down to your thermal bridge inputs, and on the right side hand table, it basically calculates like the percentage of heat flow of your various thermal bridges. So you start to see where your most impactful thermal bridges are. And you can also be looking at the lengths and quantities of your psi values and chi values. So definitely you'd want to have a discussion with if you're pursuing certification, with your PASFO certifier to determine, in their opinion, which ones do they believe need to be modeled, or, have a discussion of what are the high impact thermal bridges that will give us, the best foot forward as we progress through the design. So yeah, most of the time on the large buildings that I work with, it's going to be our floor interface with the wall, balcony transition with the wall, and especially the window to wall transitions. Like those are very important details to have both accurate information and to get that accurate information as early as possible, because it can have, as I said before, a cascading effect on the rest of our building design. We don't want to have to throw a bunch of extra insulation at the opaque assemblies unnecessarily if we actually tackle these high impact thermal bridges very early in the design stage.
Yeah, and the exciting thing is, you're the consultant, but your client, the architect, could say, "Oh, hey, I really need to take a closer look at that detail. This is just not going to fly. I need to look at something that's going to be more optimized to improve this." And I think that's really exciting that you could get the sort of direct feedback that would say, "Okay, here are the 5, worst performing details that you have the most length of on your project that you really need to focus on." So, yeah, it's super, super interesting. We are just about out of time. Do you have any final thoughts that you want to share?
My final thought is that when we created this Akira window connection, like definitely new construction is definitely applicable for that. But I also foresee this being used on a lot of the retrofits that we do, at least locally here in Vancouver. We have a lot of aging concrete buildings that are, were built in the 1950s, 1960s, and a lot of them are, continuously having all the scaffolding and everything else, wrapping it, doing a whole retrofit. And I think this would be a very good strategy if any of these buildings are pursuing something more energy efficient, pursuing the EnerPhit standard through PHI. I think the Akira window connection would be a very useful energy conservation measure to decrease how much insulation we need elsewhere to make a more balanced, thermally efficient envelope.
Mm-hmm. That's awesome. Well, I wish you luck. I think we're all excited to get the results of your study and all the different building types that you're applying it to. We're at time, so I just want to thank everyone for attending this session. If you have any questions, I think you can follow up with either myself or Cody through the conference platform. And again, thanks for joining us virtually, and have a great conference.